So welcome. In today's video, we'll be discussing the last of conduction, which is conduction with heat generation. Now, to be able to solve problems involving heat generation, what we have to remember is the basic overall energy balance for our heat. For this instance, you are given by the heat that comes in, the heat that is generated. Those two are equal to the heat that comes out and the heat that is accumulated. In the previous discussions that we have had, conduction was mainly because of the heat that comes in and heat that comes out. So generation and accumulation becomes zero. In this case, we will also consider cases where there is a heat generation and heat accumulation. Now we have to specify this, that the heat that comes in and the heat that comes out are the heats of conduction due to temperature gradient perpendicular to the surface. Now let's start by deriving the equation of our conduction with heat generation in a slab. In this case, we're given by a slab in which there is this increment, that is the infinitesimal change in x, which is dx, and then there's this center which is equal to 0. Any temperature that is outside of this slab is what we call TW, and then we have x and then negative x referencing the center of our slab. Now, if our slab has a distance of, let's say, L, this means that this is the distance from the center. I would also like to point out that when we have conduction with heat generation through a slab, we start with the center being the origin of the heat, and then the heat flows from the center going out of this certain region of the slab. In this case, if we're asked about what is the certain temperature in which, and what portion of the slab will you get the highest temperature, then you could say that it is at the center, simply because this is the one that starts with the heat generation and then it goes out until in a practical say we feel the heat that comes out from this certain slab. So let me start by deriving the equation for this using the overall energy balance. So in this case, if I have the heat that comes in, which is by virtue of the conduction due to temperature gradient, that simply means that I have to consider all the problems that we have solved using the Fourier equation. In that case, I have negative k dt over dx times the area. And this is simply what we call the Q in. Now I have to specify that the Q of generation is simply the heat per unit volume, which is the small q. If this is the heat per unit volume, I need to multiply this to the volume, which is typically the area multiplied with a certain thickness. And in this case, the thickness would be dx, simply because we cannot tell exactly what will be the value of our thickness. We could say that this is x, but sometime it could be that it has a small value of x sub 2 minus x sub 1. In this case, it is safest to refer to this as the increment of our thickness. Now let's move on with our Q out, which means that any heat that comes in should come out. So if by virtue of conduction this is just the temperature perpendicular to the surface, we could also say that this is simply equal to the heat that comes in, which is given by the Fourier equation. And lastly, what we have here is the heat of accumulation. Heat of accumulation is quite a more complex thing than heat of generation, because if we need to find the accumulation, we're actually referring to the heat that is being generated and being accumulated at this particular region. Now, in this case, if that's the same heat as what comes in or comes out, I could simply say that that heat, instead of representing it as the small q, I can just direct it to the Fourier equation, which is negative k dt over dx times the area. Now I have to specify that this heat of accumulation should be differentiated with respect to the thickness, simply because accumulation is a value that is dependent, or it can be said that as the time progresses, the accumulation starts from the center going out. In this case, the heat of accumulation would be dependent on our time, and of course, it somehow crawls from the center going out of this region. So in this case, I have here the derivative of our thickness. Okay, and since we have differentiated it with respect to the thickness, and we actually need to find the Q here, and actually this is already the Q, but if we have to like differentiate it with respect to dx, we need to multiply this with respect we need to multiply this with the thickness again, which will be dx. Now I have to specify that when multiplying this with dx, you won't be canceling this dx since they are different. This is a composition function while this is a multiplication of product. So in this case, we have to differentiate this first before multiplying this with the answer. Now we are left with the heat per unit volume multiplied with the area times the infinitesimal change in thickness, that is equal to d over dx times negative k dt over dx times the area times dx. Now we can also cancel dx out since they're just multipliers of our terms here, and now we're left with negative k dt over dx times a. We can also cancel out a since the expression here would only mean that we need to differentiate this with respect to x. In this case, k is a constant as well. So if we would be dividing this with negative k, then we're left with q over negative k, that is equal to d over dx and then dt over dx, which is equal to the second derivative of time with respect to our thickness. And in this case, we're given by the general differential equation of our heat of generation in a slab, or we could also rewrite this as d squared t over dx squared plus q over k is equal to 0. Now we will be starting the final or the answer to this differential equation in second degree by solving for this and finding t and the expression that must be used. Now we will be continuing our solution from the second order differential equation. So there are ways that we can solve this using the general solution for second degree differential equation, but what I'll be doing is simply going back to our original equation again, since this is much simpler than using the solution that using differential equation, though this is also another type of differential equation solution. So going back with this portion here, I have now to be able to solve the problem or the differential equation, I'll be integrating this with respect to dx. So in this case, I have to put a dx here, but I don't have to do it here since you can only see that this is an expression that means differentiate. So if I'll be differentiating this with respect to x and the answer, I will get the answer, simply integrating this would also mean that this is already the answer. So in this case, if I would be evaluating this, though this is not a proper way, you could just imagine this being cancelled out since they're like operation of integration and then differentiation in a composition. So in this case, I have dt over dx. This is equal to the integral of this one is simply we'll just add x here since these are just almost constants. So we have negative q over k and then x. Then we will be adding a certain constant. Let's call it constant 1, c1. Now since we're not yet done and this expression is actually separable already, so we'll be multiplying this both sides with dx. So now we're left with dt is equal to negative q over k x dx plus c1 dx. So we'll be integrating this since they already separable equations. So now we're left with t equals negative q over k, and then this one is actually times x squared over 2 plus c1x, and then another constant which is c2. So this is the final form of our answer for differential equation. We have two constants here. Now we need to find the value of these constants. Now for c1, we could just go back to this equation here. This is c1. So if dt over dx equals negative q over kx plus c1, and then at x equals 0, which means that we're typically considering the center of the slab here, where heat just starts being generated. So in this case, at any time t, the temperature with respect to our x, which is at 0, dt is still equal to 0, provided that we're just starting to generate heat. So in this case, we have 0, that is equal to negative q over k times 0 plus c1. In this case, we have c1 equal to 0. Now since c1 is equal to 0, we need to find the value of c2. So now this expression will be simplified into t is equal to negative q x squared over 2k plus c2. And knowing that c2 is this expression, so for c2, what we have here is we'll be considering the outside temperature. So let's say at L, which in this case L is the length from the center going out of the from the center to the edge of our slab here, and at that portion where from the center going to L, at this portion here, we could say that the temperature there is Tw. So in this case, when we have at L2, meaning this is equal to x, our T is Tw. So we'll be substituting that Tw is equal to negative q, and then that is L squared over 2k plus C2. So in this case, we have an initial value that C2 is actually equal to Tw plus QL squared over 2k. Now, since we already have C2 and C1 is equal to 0, let's plug in again this value of C2 to our equation. This should be here. So in this case, we'll be having T is equal to negative q x squared over 2k plus Tw plus QL squared over 2k. And then if we would simplify this, we have T minus Tw, that is equal to Q. I'll be factoring out Q and 2k here, so that is Q over 2k multiplied with L squared or minus x squared. So in this case, this is the final equation for the heat generation through a slab, where we're considering our x being 0 at the center, and L is the somewhat the half length from the center going to the edge of our slab. So if you were asked, let's say, what is the temperature at the center, actually we always refer the temperature at the center as TO. So what is the temperature at the center? Okay, so that's the question. What is the temperature at the center? So at the center, where the temperature is TO or T sub O, we have here x equal to 0. Since in the figure we've already seen that at the center here x is equal to 0. So you just have to substitute that value of x to our equation. So in this case, I'll be having T minus Tw equal to Q over 2K, and then that will be simply multiplied with L squared, since we have here X squared being 0. And now since our temperature here is referred to as TO, so what we get here is TO minus TW is equal to Q over 2K L squared, or we can also rewrite this as the temperature at the center, that is equal to Q over 2K multiplied with the square of the length, which is the half of that slab added with our surface temperature. Okay, so that's how you derive the equation for our heat of generation through a slab. And we'll be using that on our problem after we've finished deriving all the equations that we need. And of course, if you don't like deriving, you just have to memorize all of these, starting from this one and of course the center temperature. But if you find it hard to memorize the equations, then you might as well want to go through this derivation, though this is not yet a really complicated one. Now in this case, let's try understand conduction with heat generation through cylinders. Of course, we have to apply the same concept as for the slab, which is we need to consider the overall energy balance for the derivation of our formula here. Now it's the same thing. We need to find the heat that comes in, or the heat that flows in, plus the heat that is being generated, that is equal to heat that comes out, and then added with the accumulation. You just simply understand that without the energy or heat coming in and going out, you just simply cancel those out, your Q in and Q out. But for the sake of being able to understand an overall energy balance, we'll be adding them, or we'll be just substituting them using the Fourier equation. So I have to emphasize these things here, since we have here a cylinder that is solid. So that means that I have, for example, a copper wire, and this is the cross section of that copper wire. The center would be at this point, which is at TO. That is, if I wanted to find the temperature at the center, I will call it T sub O or TO. And then I have here some R, that is the radius from at this certain distance from the center. I don't know the exact distance, but it is some distance from the center. And then R, the capital R here, is the center, is the distance from the center, or exactly the radius of the whole solid cylinder that is present here. And then dr is actually the infinitesimal change in the radius, that is also equivalent to some vertical strip for our slab. So this is very essential for the accumulation or the generation. Now I also have TW here, which is the surrounding temperature, or the temperature that is experienced after some time of having this wire generating heat. And also have Q here, which is the heat that is being generated. So in that case, since we're not be dealing with slabs anymore, so our dx would turn to be dr, that is the infinitesimal change in the radius, and then our a will not be constant, simply because before we have a slab that is a slab would just have to travel the area here, and it would just be the same. But for cylinders, or solid or hollow cylinders, as the heat travels from the center, the area will be increasing, since it will have to travel the radius that is increasing as it goes further away from the center. So in this case, the area would simply be equal to 2 pi r and then some L, which is the the longitudinal area, and instead of simply writing A. Okay, and then I think that's all for that we need to understand here. So we need to find our Q in, that is simply the Fourier equation. So any energy that comes in here for our wire due to conduction, so we have here negative K dt, and then that is dr, then multiplied with 2 pi r L. And then that is equal, added with the generation of heat that is being generated by this wire. So we have the small q, meaning the heat per unit volume, and then multiplied with the area, where the area is actually equal to 2 pi RL, then multiply with the infinitesimal change in the radius, so that is dr. Now, this is equal to the heat that comes out, so that simply means that if this wire is conducting conducting heat more, even though it will be just very minimal, it still has to come out of this wire. So that is negative k dt over dr, and then 2 pi RL. And then of course the accumulation would simply be from the center going out of this solid cylinder here. So what we have here is simply heat of conduction, that is negative k dt over dr, times our area, which is 2 pi RL. And we need to differentiate this with respect to our radius because it is increasing from center going to R, capital, and then multiplied with some thickness of a radial thickness, that is dr. So we're pretty much done with the substitution. Now let's try simplifying these expressions. Now we have here, can cancel this out since they are the same, and then we have to analyze this further, this expression more. Now before, we have a being a constant, and since a doesn't have any expression that is with respect to x, we can just factor them out. Now since we have here r, what we are left that we can just put right in front of our equation, or this term, is our 2 pi L and negative k. So I'll be rewriting this as q times 2 pi RL from this expression times dr, that is equal to negative k times 2 pi L, and then multiplied with the derivative of dt over dr, and of course times dr. So in this case, I can now cancel out the multipliers for each term. This one is that should be just 2 pi L and then 2 pi L. Okay, now I'm left with q r over negative k, since I'll be dividing both sides by negative k, and then d dr, and then dt over dr. Sorry, I forgot to add r here. So multiply with r. Actually, r come from this portion. Now, since this is actually the differential form, I can now integrate this. So I'll be integrating this with respect to the differential change in radius, so that is qr over negative k dr, that is equal to the integral of d over dr times dt over dr r. Now we have here dr, so we can just simply take out q over negative k and then multiply with r squared over 2. That is equal to, since this is the antiderivative and this is the derivative, we're left with what is inside this component. So we have d over dr times r, and of course, since we use differential equation here, we need to add a constant of integration. So now that I have this expression, I'll be dividing both sides by r so that I can actually separate the variables. So in this case, I have q times r over negative 2k, that is equal to dt over dr plus c1 over r. And now I can multiply both sides by dr to finally separate the equations. So what we'll get here is qr, or negative qr dr over 2k, that is equal to dt plus c1 over r. Now let us integrate them, each of the term. So now we're left with the answer, that is negative q over that is r squared over 2, but we have 2 here, so that will be multiplied with 2, so we have 4, and then k, that is equal to t plus c1, 4k, that is equal to t plus c1, that is ln of r, and then of course plus the second constant here. Now, this is our final form or the final equation for the heat of generation through cylinders. Now, there are cases when cylinders are hollow or solid. Now, if in the case we have a solid cylinder, so we have a solid cylinder. So, in the solid cylinder, what we have here is that if R is equal to 0, and we know that at that point, dt is also equal to 0 since we're just starting to have the differential change in temperature. So in this case, if that is equal to 0, we could simply say that in this portion here where we have, let's see, this C1, so we have there the Q over negative 2K times R, and then that is equal to dt over dr, that is actually R squared, and then R plus C1. So in this case, if R is equal to 0 and then dt is equal to 0, what we have is 0 is equal to 0 plus C1, and C1 is equal to 0. So in this case, if we have some solid cylinders, this expression will be simplified into negative QR squared over 4K and then equal to T plus C2. Now, using the initial value or the final value for our C2, since after some time, what we get is that since if R is the outside radius, what we get at the temperature is our TW, which is the surrounding. So you can see here at the figure, if R is equal to the capital R, which is the outside radius, our temperature is TW. So substituting that with our equation, what we get here is negative Q and then capital R squared over 4K, that is equal to TW plus C2. And going back to our equation where we will substitute C2 here, what we get is simply negative QR squared over 4K, and then that is equal to our T plus, so C2 here would be equal to, actually that should be minus, equal to T minus, since this one is C2, so Q R squared over 4K, and then if we need to transpose this, that would be negative TW. So in this case, I have here, and this whole expression is actually C2. Okay, it's just negative. So in this case, I can also rewrite this as T minus TW, that is equal to Q R squared capital over 4K minus Q R squared small over 4K. And then we can simply factor out Q over 4K here. So we're left with R squared minus R squared. So this is the final equation for the heat of generation through solid cylinders. So remember, this is just for solids. So it will be different for hollow cylinders since the center would not be the one that is hollow, but actually the one that is actually the middle of this portion here. So you will be deriving that based on this expression. Now in this case, let's just analyze that if R is actually equal to 0, we're referring to the temperature which is equal to the center temperature. And in this case, that is equal to TO minus TW, that is equal to Q over 4K, and since small r is 0, we're left with R squared here. And this final expression here is for our center temperature, that is QR squared over 4K, and then plus the temperature at the surrounding. So there we have it, and then of course the center temperature for this wire is actually the maximum temperature. So if you want to challenge yourself, you can actually try to derive the equation using solid spheres and hollow cylinders if you want. To be able to get a good grasp of heat of conduction with heat generation, let us solve this problem. I want you to pause the video and go back here after you've understood the problem. Okay, so now we are asked to find the center temperature for A. To find the center temperature if the air is at 25 degrees Celsius, and we have to neglect the effects of convection. Now I want to specify or point out that it is important to neglect the effects of convection simply because if there is a convection here, the computation would have been different, and of course, since we've not yet discussed convection, so we don't have to incorporate the effects of this type of heat transfer. So that for A, we can now solve this by simply using our equation that we have derived before. So basically, I will not be deriving again since we've already done that. So if you have memorized the equation, so it is the best thing that you have to do. Okay, but of course, if you've forgotten the equation, then you might as well want to derive it again. But anyway, so let's just write the equation. So we have there T minus TW, that is equal to Q, which is the unit per, the heat of generation per unit volume over 2K, since this is 2K since this is a metal slab, and then multiplied with L squared minus X squared. Okay, so this is our general equation, and remember, let's just draw some figure so that we might not get confused. So X here is equal to 0, and this is what we call L. Okay, and of course the distance or the total thickness of this slab would be 2L. So in this case, I need to find this center temperature, and we've mentioned before that center temperature is equal to TO. So since we need to find the center temperature, all we have to do is substitute T with TO, and given TO, we know that X here would be 0 since it is at the center of this slab. So with that, our formula simplifies to TO minus TW equals Q over 2K, and then simply L squared multiplied with L squared. Now we can simply substitute the values here. So we have TO, that is equal, let's just transpose it here. So now I'll be substituting the values here. So I have Q, which is, so we have to always check on the units of our given here. So it should always be in SI unit and MKS. So with that, we have here Q, that is 10 to the 8 watts per cubic meter. So we have 10 to the 8 watts per cubic meter. Divide, let me just write TO here, or T sub O. Then we have Q over 2K, so we multiply this 2 with the thermal conductivity, so the unit is consistent. And then, we need to multiply this with L squared, so that is times L squared. So the thickness is 30 mm. So in this case, that simply means that we have 2L, which is equal to 30 mm. So remember, the thickness that we're considering when we have a slab is basically the distance from edge to edge of this slab. So this one is the 30 mm. And if we need to simply find L here, all we need to do is divide this by 2. So we have 15 mm. So 15 mm to the right side, and then 15 mm to the left side. And in this case, we need to convert this to the MKS unit. So we have 15 mm, then we multiply this with 1,000, 1 over 1,000. That is 1 meter. Okay, and then so what we get here is in meters, and then we need to square it, so we have to square that, and then we add the surrounding temperature, and the surrounding temperature here is our TW, and it says in the problem that is 25 degrees Celsius, so that is 25 degrees Celsius. Now, we have we can actually convert this to Kelvin, or we can also not convert it, simply because if we are to like convert this to Kelvin, let me just add something like this so that it is in Kelvin. If, for example, I have TO here, and that is, for example, I have blank TO plus 273.15, it will be cancelled out here because this is simply the change in temperature. So even though you don't convert this value to Kelvin, you will still get the correct answer. But of course, since we are considering Kelvin here, if you could see here from the dimensional analysis, it is better for you to convert this so that we can logically add the two values. Because if this is in degrees Celsius and this one is in Kelvin, then although this is a change, you can already add that, but basically we're just following the guidelines in adding magnitudes with units. So I suggest that you still convert it. So with that, our answer would be equal to might well want to try to solve it also so that you can check your answers. So what I will be getting here is 748.15 Kelvin. So this is 475 degrees Celsius. Okay, so the answer, or the temperature at the center, is really high. Well, simply because this one is actually a heat exchanger, so it is expected you'll be getting a very high temperature there. Now, you can express your answers in degrees Celsius and Kelvin. I don't mind, but of course you have to like consider the Kelvin first in computation, since it's more logical to be using that unit first. Okay, so now let's try letter B. So for letter B, it says here that we'll be adding something like a sensor here. So if let's just do it here. So we'll be putting something like a sensor here, a temperature sensor, and then this temperature sensor needs to measure something like 212 degrees Celsius. So most of the time when we have a heat transfer equipment, we're always adding some sensors like the temperature sensors, simply because we have to track all the temperature changes that we have in order to maintain that equipment. So in this case, we'll be adding some temperature sensor, but in this case, it will be placed directly on our metal slab that is used to generate heat. Now, the question is, what will be this particular distance here? So what is that distance? Okay, and knowing this is L over 2, we can actually solve it by using the original formula that we have here. So we have T minus TW, that is equal to Q over 2K, and then L squared minus X squared. So remember, X squared is equal to 0 at the center. So in our previous computations, we've already neglected this X squared term. But now, since we have this, we need to find the location from the center, then X squared should be included. And of course, since we have here a given of a temperature of 212 degrees Celsius, and of course we'll be neglecting the effects of convection. So with that, we have a temperature that is equal to 212 degrees Celsius. Oh, I forget to write the air temperature. The air temperature should also be 25 degrees Celsius. Let me add it first. So the air temperature is at 25 degrees Celsius. And I wanted to oh, never mind. It's already included here that we need to neglect the effects of convection. So anyway, so we have T, that is equal to 212 degrees Celsius, and then TW, that is equal to 25 degrees Celsius. So all we have to do is to simply substitute the values here. So now I'll be having 212 degrees Celsius. Now this is what I've been telling you before, like this one. You can add some 273.15 here so that we can get a Kelvin that is consistent with the units at the right side. But since we'll be subtracting this T minus TW, can actually not convert this portion so that, to simplify the calculations. Because in here, we could just simply see that it can be directed that 273.15 will be subtracted with each other. And the difference in these two is that this is the temperature alone here, and we need to convert that in Kelvin simply because the temperature here is in Kelvin. We don't have any 273.15 Kelvin here that will be cancelled out. Okay, but in any case, if you still want to check on and use the correct, the appropriate units, although this one is also correct, you can still convert that to Kelvin. So we proceed, that is Q over 2K. So we'll be using the same Q, that is 10 to the 8. Well, that is 10 to the 8. I won't be writing the... okay, let's just write the unit. That is 10 to the 8. Let me write it again. It's 10 to the 8 watts per meter cube, then divided by 2 times the thermal conductivity, which is 25, and then watts per meter Kelvin. And then this will be multiplied with L squared, and L is actually this should not be L over 2, sorry. This should be L. Okay, so our L here is the same for our previous one. We have 15, so we have 15 mm. Then we need to convert this to then square it and then subtract x. And then if you wanted to have an answer that is already in millimeters, then we can now simply divide this by 1000. So we'll be getting mm. Okay, so x here would be the distance from the center. This x here. So what you'll be getting is simply the distance from the center. And then you can just use your shift solve function to get x. So I'll be using mine. So let's solve for it. Okay, so the value of x is simply equal to 11.4673, and that is in millimeters. Okay, so if you've forgotten to add or divide this portion with 1000, then you'll be getting the answer in meters. Now, if you added some 2 here, what you'll be getting is actually the distance from if the distance that is at 2x, that simply means that you have x here and then you also have x here, and then when you combine those distances, then you'll be getting that value for x if you added something like 2 here. But you don't have to add, since x here is already the distance from the center. The answer would be 11.4673. So in that case, if you wanted to to summarize, to get a measurement of 212 degrees Celsius from the sensor that we'll be placing, you need to place it 11.4673 mm units from the center. Okay, so that's how it works for heat of generation through slabs. And I wanted to specify something here, since we've already given by we've already given with the thermal conductivity, and we are assuming that this is constant along the temperature. Now, if K is given using a differential equation, we have to go back to our original equation and we need to start deriving again and formulate the new formula for this. It will be kind of difficult for such cases. And if K is given in terms of T, for example, K here will be given in terms of T and not in differential equation, then you can simply substitute that equation to this expression since it is given in T and we don't have any differential equation. Okay, so at least that would be more, simpler than deriving the equation again. So probably I'll be giving you some kind of sum for that, but I will not be prioritizing it since my priority would be discussing radiation and radiation and convection first. Okay. Now let us try solving for another heat generation problem. So in this case, I wanted you to pause the video and read the problem again and understand it and go back here after you've understood the problem. Okay, so while you're reading it, let me just draw some figure here so that we can visualize it. I'll be drawing a cross section of our rod, and basically what we have is a really rich man here, which is a billionaire, and he wants his mansion to have a silver wiring. So this copper rod with the cross section here actually is a silver, and what we have here is simply the heat that is being generated per volume, that is 1.2 times 10 to the 11 British thermal unit per hour, feet cube, and then the temperature of the surrounding. So that simply means that we have TW, that is equal to 15 degrees Fahrenheit. So we'll be solving this in terms of English units. Now the rod measures 0.025 inch diameter. So this is very important since we've been using radii before, and in this case we're given with what we call this the diameter, and we know very well that diameter is just 1/2 of this, 2 times the radius. So this one measures so the diameter measures, actually let's use a capital D, 5 inch. So if you need to take the radius, then we need to just simply divide this by 2. I'll be dividing this, so that is 0.0125 inch. Now it also says here that we need to neglect the effects of heat, the convection, and then we take K as a constant along the center to surrounding temperature. So K is constant. So if we have the center to surrounding temperature, so you could say that K is constant at, from TW to TO. So that only means that K will not be changing from our TW to TO. So the first question, or the first that we need to solve for, is the maximum temperature. So we know very well that this is a solid rod, which simply because this is silver wiring and a wire is actually a solid cylinder. Now let me just draw the center. Okay, so that is the center, and if we need to find the maximum temperature, where do you think would that maximum temperature lie? Well, simply because this is generating heat, the flow of electrons will simply start from the center. The heat flow would start from the center and it goes out to the outer edge of this cylinder. So in that case, our maximum temperature exists at the center of our solid cylinder. So remember that when we have a solid cylinder, the maximum temperature exists at the center. The same goes for our slab. So since it's, of course, it is a solid, usually for solid materials, the maximum heat exists at the center, but this would be very different if we have a hollow cylinder. If this is hollow, then the middle portion would be empty, and since there's no heat there, the maximum temperature would lie somewhere along the above the empty region and just below the outer radius. But anyway, we'll not be solving for that. So solid cylinder is at center, the maximum temperature. So with that, let's just write again the formula. We have T minus TW, that is equal to Q, that is the unit per, the heat per unit volume, and then 4K for our solid cylinder multiplied with the capital R squared, which is the outer radius, minus R squared. And R squared is actually not the inner because we don't actually have inner radius, but R here is the distance, any distance from the center which is not R. So in this case, if we just need to find the maximum temperature, R would be 0 since that is at the center, and then T would be equal to TO. So with that, let's have TO minus TW, that is equal to Q over 4K, and then simply multiply it with R squared. Now let's just substitute the values, and since we have Q and R, we've got no problem with it, but we don't have K yet. But it says here that K is constant from TW to TO, so I can now evaluate K at the surrounding temperature since it's already constant, and TW for this problem is given. So I need to find the thermal conductivity of silver at 15 degrees Fahrenheit. So I'll be using the Paris handbook again, and this is already opened here. So this is the thermal conductivity temperature table for metals, and you need to find here the silver. And silver here is, yes, after the silica, we have a lot of values here, and since we have a lot of values, we need to consider the temperature that is given. It says here these temperatures are in Kelvin, so I need to convert this first to Kelvin so that I can use this table of values. Now 15 degrees Fahrenheit in Kelvin is equal to, I'll be using the functions in calculator. I'll be converting this Fahrenheit into degrees Celsius. So I have like negative 9.44 degrees Celsius, and this is actually cold. So imagine this billionaire is literally living in a very cold place, like, I don't know, Antarctica, joke. Anyway, so we have negative 9.4 degrees Celsius, and I'll be converting that to Kelvin. So I'll be getting 263.7056 Kelvin. And I would also like to specify that if you really have a very low temperature for your surrounding, assuming that K would be evaluated at that temperature, you'll be getting a very high thermal conductivity simply because silver is a good conductor of electricity. And remember, when you have a low temperature, you'll be getting a high thermal conductivity, since that's basically the behavior of thermal conductivities for good metals. So we'll be having 263.7056. Let's take a look here. So we'll be interpolating between these 200 and 300 values. So that is around here. So we'll be getting the values from 430 and 425. So we only have around 5 unit difference, but of course we have to consider that, and I'll be interpolating, so might as well interpolate. So for 100 we have 430, and for 200 we have 425. So use your knowledge in interpolating. So what I got here is 421.8147. So I wanted you to always take a look at the units, since you might led wrongly with this. You might get confused with the units, but we need to read the table. It says here that thermal conductivity is tabulated in watts per meter Kelvin, so this value would be in watts per meter Kelvin. And remember, we'll be solving this in terms of English units since most of the units here are in English, so we need to convert this to English. So that is K will be divided to the factor for our conversion for English, which is 1.730735. So of course you can still do the basic, like deriving all of this from BTU to calories and all this stuff, but of course I will not be doing that again. So we have K equal to, and remember, if you have British thermal unit expression in K and you want to convert that to watts per meter Kelvin, you'll be getting a higher value. So in this case, since we'll be doing the reverse, we'll be getting a smaller value here. So we have 243.71. That is actually 7199, so let's just do some 7200 British thermal unit per hour, and then that is feet, and then degrees Fahrenheit. Okay, so now we have completed all that we need, so let's just try to substitute the values here. So we'll be getting TO, and we need this value here. So TO is equal to Q. Our Q here is 1.2 times 10 to the 11th power. So that is 1.2 times 10 to the 11, that is British thermal unit per hour, and then that is cubic feet. And then divided by 4 times the thermal conductivity, that is 243.7200 British thermal unit per hour, feet, degrees Fahrenheit. And then we need to multiply this with our r squared, and our r squared is simply, from the r here we have 0.0125 inches. So we have 0.0125 inches. And remember, since this is in inches, we need to convert this further into feet. So we have 12 inches per 1 foot. So that is, we have to square it, since in the formula we need to square it. And then of course, since I have to transpose this to the right side, so we need to add the TW. And TW is the surrounding temperature, that is in 15 degrees Fahrenheit. So I have 15 degrees Fahrenheit. So now I have my TO, and that will be our final answer. So the answer at the center temperature is 148.5635 degrees Fahrenheit. So to make a good grasp of the value that is equal to this, let me just convert this to degrees Celsius, but you don't have to do it. I just wanted to get a feel of what is it in terms of degrees Celsius. So that is 64.7575 degrees Celsius. Because I don't know, it's easier for us to get an idea of how hot an object is in terms of Celsius or Kelvin. So in this case, it's just 64.7575 degrees Celsius. And remember, since this is wiring, we're actually we don't actually want to have our wiring to give a really high value, since it will generate heat. It will generate fire instead of heat if it will be having a really high temperature. But of course, since this is silver, it will just will not burn easily. But of course, if you have an insulation that is located at the outer covering of the silver, since this is a wiring, you need to minimize the heat effects of that by simply having this temperature maintained at around this kind of temperature. But of course, if you get a really high value for a problem and you've already done the correct calculations, then that's it for that problem. I mean, I'm not restricting all the answers to just this kind of answers, but what I'm telling you is that in a logical way, sometimes you can apply the idea of having the scenario based on the problem. Like, for example, this one. This is a very high temperature, but we're actually having this kind of heat exchanger, and that is to be expected on a heat exchanger. So anyway, let's proceed with letter B. So letter B here says that we need to determine the mid-radius temperature. So when we talk about mid-radius, for letter B, what we have is T at, let's just do something like TMR. So this TMR is the temperature at the mid-radius. Of course, you're free to use any kind of designation for that. Now, mid-radius is, if we wanted to draw that mid-radius somewhere in our figure here, we'll be doing something like this portion. Simply because, since this is the radius and this is the whole radius, if we wanted to take the middle of that radius, we just need to take the 1/2 of that radius. So in this case, so we need to find this one, and then the mid-radius would be equal to simply 1/2 of the radius, and that is equal to 1/2 of 0.0125 inches. So our mid-radius is located at 6.25 times 10 to the negative 3 inches from the center of our rod. Now, in this case, I am asked to find the temperature at the mid-radius. So, we're not dealing with the center now, we'll be dealing with this mid-radius. So, we'll be using the same formula again, the one that we used at the first part. So, we have T minus TW, that is equal to Q over 4K, and then multiplied with the outer radius squared minus whatever R that we have here. So to be able to find the TMR, so we get here TMR minus our surrounding temperature, that is 15 degrees Fahrenheit. So we have here 15 degrees Fahrenheit, that is equal to our Q over 4K. So we've already written that. So Q over 4K. So let me just, take a snapshot here, and then won't be writing it again. So we have here something like this, okay, and I can just move it, sorry, okay, let's just move this so that we can have a clearer view of this. So we have TMR, that is minus 15 degrees Fahrenheit, that is equal to this Q over 4K, that is Q, and then we have 4 and then K. K is still the same since we're basically dealing with a constant K along the center temperature to the surrounding temperature. So whatever distance from the center you'll be evaluating, it will still be the same. So multiplied with R squared, and R squared, remember, is 0.0125. That is 0.0125, and we need to convert this to feet. So divide by 12, that is squared, and then minus 6.25 times 10 to the negative 3. So negative 3 divided by 12, and then that is squared. Okay, so yeah. So that is our mid-range temperature. So let's just use our calculator to solve for it. Now I want you to solve with me so that you can always check your answer. Since I'm doing this something like, not really the first time, but I've already solved this, but of course sometimes I get too carried away with solving. So I've obtained a value of 115 0.1726 degrees Fahrenheit for this. So one way to check your answer is to simply look at the center temperature. When we say center temperature, we're actually dealing with the maximum temperature. So we have 148. So your answer should be less than 148 since that is the maximum temperature, and of course greater than 15. So by that notion, we can say that our answer is possibly correct since we've already obtained that answer that lies in between these two values. But of course, the best way to check your answer is to actually solve for it again, and if you get the same answer, so that's the correct answer. But in a more logical way, if you're not having this doubt in your computations or writing at your calculator, then evaluating it with the idea that it should be in between those two values, then you'll be able to get the correct answer. So I think that's really the correct answer. I've checked it twice. So with that ends our heat of generation, and I hope you've understood this. Actually, this is an easy problem, and the more confusing part would if K is given in terms of differential equation, as I've mentioned before, but I don't think I'll be giving something of that kind. Probably the most difficult that I'll be giving you would be that K is equivalent to something like, for example, K is equal to something like a function of T. So for example, K is equal to like 4.817 T plus, let's say, 4.6. So in this case, you don't have to like differentiate again then derive. You just have to simply plug in this K to this K here, and then you won't be getting K, you'll be using the temperature here. That should be temperature only. So I don't think that's really difficult. You just have to substitute that value from this case. Since actually I have to specify that these problems are not really that more often appearing in board exam than in conduction, because those that we've solved before, the series conduction and all the convection, they are more often appearing on board exam than this kind of problem. But of course, sometimes these appear too. Okay, so now that's the end of our conduction. We'll be starting with convection in our next video. Okay, so thank you.